We have two ways to implement a graph in code. In this video, we're going to talk about the first approach, and we'll look at the second approach in the next video. One way to represent the edges in a graph is using a matrix or a two-dimensional array. Using this matrix, we can see how nodes are connected. So for every node in our graph, we're going to have a row and a column. If two nodes are connected, we mark their intersection with a 1 or a true. So here we can see that John is connected with Mary, Bob, and Alice. This is what we call the adjacency matrix. It's fairly easy to implement. All we need is a two-dimensional array. But the problem with this approach is the amount of space we need to allocate for this matrix. If we have n nodes, our space complexity is going to be n squared. That can grow very fast. For example, if we have 1,000 nodes, our matrix is going to have 1 million entries. The approach we're going to explore in the next video will solve this problem. But let's continue studying this approach because it has its own merits. Now let's talk about various operations we need to perform and their time complexity. If you want to add a node, we have to allocate a new matrix with one extra row and column, and then copy all the existing items in this matrix into the new one. How many entries do we have here? N squared. So adding a new node is an expensive operation and runs in O of n squared. Now we could optimize this by pre-allocating a large matrix so we don't have to copy all these items every time we add a new node. But again, this is going to waste memory. Also, when talking about graphs, we prefer to express the time complexity in terms of V, which is the number of vertices or nodes in this graph. As you will see later, the time complexity of certain operations also depend on the number of edges. So we use V and E instead of N when we do complexity analysis on graphs. Now, what about removing a node or a vertex? Again, we have to allocate a new, smaller matrix and copy items around. So we have O of V squared. What about adding an edge? Let's say we want to add an edge between Alice and John. First, we need to find the index of these nodes. We can use a hash table to store our nodes and their indexes in the adjacency matrix. So in this hash table, we map our nodes to their indexes in the adjacency matrix. If you want to add an edge between Alice and John, we find their indexes using this hash table. That's an O of 1 operation. Once we have the indexes, we can quickly go to the corresponding item in our matrix and turn it on. So adding an edge is pretty fast and runs in constant time. What about removing an edge? It's the same as adding an edge. We have to go to a given entry in our matrix and set it to false. How about checking to see if two nodes are connected? We want to see if Alice and John are connected. Again, we look up their indexes and read the value of the corresponding entry in our matrix. This is an O of 1 operation. Another operation we need frequently is finding all the nodes adjacent or directly connected to a node. That means the neighboring nodes. In this matrix, how can we find the neighbors of Alice? First, we have to use our hash table to find the index of Alice in our matrix. Now we need to look at every item in this row to find the connected nodes. How many items do we have in this row? That is equal to the number of nodes or vertices. So finding the neighbors of a node runs in O of V. And that means if we have 1 million people or nodes in this graph, and John is connected with only 3 people, we have to check the connection between John and all the other 1 million people just to discover his 3 connections. So overall, the adjacency matrix requires a fair amount of space, but performs well if we need to add, remove, or query the existence of an edge. Finding the neighbors of a given node is a bit slow and runs in linear time. Adding and removing a node are the slowest operations and run in quadratic time. So they're suitable if you know ahead of time how many nodes you're going to need, and you're not going to add or remove nodes often. In the next video, we're going to look at another approach for representing a graph.